My name is Marcin Hoffmann, and I'm a Technical Solution Manager with Rimedo Labs. Today I'm happy to introduce you to the topic of Open Run for jamming detection and mitigation in a live testbed. This work was done by me, together with two R&D experts from Rimedo Labs, Dr. Łukasz Kułacz and Professor Paweł Kryszkiewicz. Before I introduce you to the Rimedo Labs proposition of jamming detection and mitigation in Open Run, let me say a few words about myself. As a Technical Solution Manager, in Rimedo Labs I'm responsible for leading ORAN software development and R&D projects covering areas like resilience, energy savings, traffic steering, or massive MIMO. In parallel, I'm a PhD candidate with the Institute of Radiocommunications Poznań University of Technology, focusing on the utilization of AI/ML for intelligent network management. Feel free to reach me through the QR code to my LinkedIn profile on the right. To begin with, the jamming attack on either a civil or military mobile network is expected to be common both during a full-scale war and hybrid conflicts. It can significantly increase the latency of packet transmission due to the injection of unexpected interference into the network, which causes frequent packet retransmissions. This can be the most harmful for ultra-reliable low-latency communications like military or industry systems. Most importantly, the jamming can be easily realized by attackers using cheap off-the-market electronic components. Therefore, there is a need to equip 5G networks with a dedicated mechanism to detect and mitigate jamming, especially under warfare conditions. A key enabler for the deployment of such algorithms is the Open Run architecture. It comes with a Run Intelligent Controller named RIC, which can host third-party algorithms deployed as JD-xApp and fed them with physical layer measurements using dedicated interfaces. In this context, Rimedo Labs proposes a Jamming Detection JD-xApp, first to detect harmful jamming, second to reduce its negative impact on the latency. Let's now dive into the deployment of Jamming Detection JD-xApp within the ORAN architecture. As can be seen in the figure on the left, the Jamming Detection JD-xApp is hosted by the near real-time RIG for fast millisecond-grade interaction with RAN through the E2 interface, or more specifically E2 lower layer control service model. The JD-xApp utilizes the E2SM LLC report style for monitoring of the hybrid automatic repeat request and MCS statistics in order to detect anomalies indicating the occurrence of jamming. The state-of-the-art approach to mitigate the effects of jamming is to switch the communications to another frequency. However, this causes a delay related to handing over connected devices, and potentially when done often, can destabilize the network. In contrast, Rimedo Labs proposes to mitigate jamming effects with JD-xApp by modifying scheduling parameters through E2SM LLC Control Service Style 2, Scheduling Parameters Control, for example MCS allocation. Optionally, as visible in the figure, the Jamming Detection JD-xApp can cooperate with a data analysis module placed in non-real-time RIG, and providing JD-xApp with a dynamic threshold for jamming detection based on the long-term performance metrics obtained over the O1 interface. For example, MCS distribution, downlink packet loss rate, or downlink packet delay. To better understand the principles of operation of Jamming Detection JD-xApp, let's look at the message flow diagram presented here. By default, the base station or E2 node transmits the data to the UE following the dynamic scheduling, for example dynamically adjusting allocated MCS or bandwidth. At the same time, Jamming Detection JD-xApp placed in near real-time RIG is capturing the hybrid automatic repeat request statistics through the E2 interface. Then these statistics are analyzed by Jamming Detection JD-xApp with a focus on the number of acknowledgements and negative acknowledgements to detect a jamming attack. In contrast to the state-of-the-art solution, the Jamming Detection JD-xApp proposed by Rimedo Labs mitigates the negative impact of attack on the network by setting a constant MCS for a given protection time through the E2SM LLC. We will show that this approach allows for a significant delay reduction in the presence of jamming and maintains seamless connection of the UE to the network. After I have covered the logic which is behind the Jamming Detection XApp, I would like to introduce you to the testbed which we use to evaluate the proposed solution. The testbed utilizes an Amarisoft base station CUDU with attached software-defined radio USRP B210 acting as a radio unit. As demonstrated in the top left picture, the Amarisoft base station is running on the PC together with a rig-like platform based on the Amarisoft API hosting Jamming Detection XApp. The Amarisoft base station provides network service to the Samsung 5G smartphone with installed iPerf to enforce stable traffic demand, as visible in the bottom. The jammer is realized with another software-defined radio USRP B210 attached to the PC running a dedicated program, as visible in the bottom right. Let's now go to the live demonstration. At first, I would like to introduce you to the lab setup. Here we can see a PC with attached USRP B210 running the Amarisoft base station together with a rig-like platform hosting Jamming Detection XApp. A few meters away we have placed the UE. Finally, here we can see another PC with an attached USRP B210 acting as a jammer. In addition, we used hardware and USRP B210 based spectrum analyzers to track the transmitted waveforms. Let's now dive into the KPIs panels related to the Jamming Detection XApp and Amarisoft base station. On the left side we see a Grafana plots. First allows us to monitor the signal-to-noise ratio for the UE. Second plot is related to the cycle redundancy check. Note that low CRC causes retransmissions and as a result increases packet delay. Finally, the bottom plot exposes the decision of the Jamming Detection XApp on whether a jamming was detected, indicated as 1, or not, indicated as 0. On the top right side, there are logs related to the Amarisoft base station. On the bottom right side, there are logs related to the rig-like platform hosting the Jamming Detection XApp. Let's start the evaluation from the reference scenario without jamming. Take a look at the OFDM waveform in the bottom right corner. Under this scenario we can see high SNR of about 25 decibels, high CRC of 1 in almost all cases, high uplink MCS for UE, around 25-26. Most importantly, as can be expected, the Jamming Detection XApp does not identify any attack. Now we focus on the scenario when jamming is present and the Jamming Detection XApp is operating, but its mitigation features are disabled, so we can see the negative effects of the attack on the KPIs. Note that the waveform presented in the bottom right corner is much disrupted compared to the scenario without jamming. While having jamming with a gain of about 40 decibels, we see a significant drop in the KPIs. SNR drops from about 25 to only 10 decibels. Uplink MCS drops from 25-26 to only 6-10. And we see a CRC drop to 0.8, which means that about 20% of packets required retransmission, increasing the delay. However, the dropdown at this stage can be identified by Jamming Detection XApp as poor network performance, for example high intercell interference. Let's now increase the jamming gain to 50 decibels, which can reflect very challenging conditions of a conflict or some sabotage activities, which as we can see causes even more drastic waveform degradation. Now the SNR drops to 0, CRC to 0.2, meaning that about 80% of packets require retransmissions. Finally, MCS drops to only about 1.3. Under such circumstances, the Jamming Detection XApp identifies the security threat. Note that under the operation of jamming, both CRC and MCS are not stable, affecting the performance of the UE. Now let's move to the final scenario, where we demonstrate how the Jamming Detection XApp proposed by Rimedo Labs can overcome these issues and provide UE with a stable connection even in the presence of the jamming. We start without jamming and high values of SNR, CRC and MCS can be observed. Now we introduce the jamming attack with a gain of 50.4 decibel, But now Jamming Detection XApp has enabled the mitigation features. The constant MCS of 1 is set by the Jamming Detection XApp for a protection period. Although the SNR is still at the low level of about 0 dB, as we cannot easily remove the jammer, the CRC now has a high value of 0.9, meaning that instead of 80% of disrupted packets, we only have about 10% now. After the protection period expires, the Jamming Detection XApp restores the default MCS allocation. But the jamming is still present, so after the short time it becomes detected and mitigation mechanism is triggered once again. Finally, after the next protection period expires, jamming is no longer present and the base station is restored to the default setting, and UE has high SNR, MCS and CRC. Let's now discuss the results that we obtained under the demonstrated testbed after longer observations. In our paper, published in IEEE Communications magazine, we used the demonstrated testbed to examine the packet delay with the presence of permanent jamming and K-jamming. Half of the time jamming is present, half of the time not. In both cases, we compared the results with the Jamming Detection XApp enabled and disabled. Here we can see a CDF plot of packet delays. When there was no jamming, blue solid line, the delay of the majority of the packets is about 40 milliseconds. The first interesting observation is that the K-jamming, marked with the solid black line, is more harmful for the network compared to the permanent jamming marked with the solid red line. The former causes a delay of up to 199 milliseconds for 95% of packets, while the latter only 80 milliseconds. The most important observation from the experiments is that the Jamming Detection XApp can reduce this delay to about 56 milliseconds for 95% of packets for both types of jamming. This can surely enable the operation of some of the communication systems even under warfare conditions. The conclusions can be formulated as follows. The Open RAN architecture enables the deployment of intelligent jamming detection and mitigation mechanisms. The Jamming Detection XApp by Rimedo Labs utilizes Open RAN interfaces to detect jamming by monitoring hybrid automatic repeat requests and mitigate its impact on the network by modifying MCS. The evaluation of the Jamming Detection XApp under the live testbed shows that it can reduce packet latency from up to 199 milliseconds to about 56 milliseconds in the case of 95% of packets. Thank you for your attention, and now I'm open for your questions. If anybody would like to reach me after the conference, please find the QR code to my LinkedIn profile on the right.